right, I'm going to try this again. I don't know what happened with that first link, but I'm going to send the new link out to announcements just a moment. I'm getting this link out to both classes, so give me a moment here. Okay, got this link out to both sessions. We'll see if this actually lasts this time. I'm not sure what happened on that, but just got to give this another try, and hopefully we can get through the work we wanted to do today. Looks like it's going to continue streaming here this time, so I'll see what we can get. All right, hopefully these announcements get through to people if you're trying to watch live. The first stream kind of crashed on me, and let's see what happens this time, but this looks like it's up and running. So let me try to get back to what we were doing here. Technology. All right, so hopefully you're joining us at some point here. I don't know what happened to that first stream, but we're I guess we're up and running on this one, and we're looking at exponents. We have a different kind of exponents now, so I'm trying to put it into this context, into the setting of what exponents were before, and the rules that we had before still apply, but they look a little different now, or they're going to when we have fraction exponents going on. So negative exponents, we already had to mess with the rule a little bit, that the 2, if you have a negative exponent, this was a 3. Positive exponent just means how many. Negative exponent still means how many x's there are, but they're in the... All right. Sorry, they're in the denominator. The negative exponent means the reciprocal of x times x. So it looks like that. We've done a little bit with negative exponents, not a lot. But that was an extension of what the exponent means. This is going to have to be a little bit different now, because if I have something like x to the 1/3, well, it's not a how many number anymore. I can't have 1/3 of them, or it doesn't really make sense with the repeated multiplication idea. Right, so that's our big question. What exactly is that going to mean if I have a fraction sitting there instead of a whole number or a negative number? I have a fraction now, and I got to think about what that means. But there's one familiar rule that helps us make sense of this. So there was some explanation of this going on before, and well, that you may have seen online, but I'm going to try to explain this here also. The rule that we have used before was how to handle situations like this. If I have exponent on the parentheses, right, like this. So x is raised to second power, and that expression is raised to the 5th power. That means x squared is multiplied by itself a bunch of times, and if you work through that, you're going to get 10 of them. It's x squared times x squared times x squared times x squared times x squared, total of 10 x's multiplied together. So we had this rule that when this happens, you can just multiply the exponents because there's 5 of them. That's just 2 times 5 gives you 10. That's how you would simplify that expression and write it with no exponents, with only one exponent. So if that rule is still going to be true for this new kind of thing, then not knowing what x to the 1/3 is, so I'm still kind of puzzled about that, but my property about multiplying exponents says if I do this to the third, then I should get x to the 1, which is just x. So my question, I want you to think about the question mark right there and the properties that are going on. And what we have is, whatever that question mark is, when I cube it, it comes out to 1. So it is the value that when I cube it, it comes out to x. That's exactly the name. That's exactly what we mean by the cube root of x, is the thing that when we cube it, it comes out to x. So that's got to be what this expression is. I mean, to be consistent with the other rules that we have out there, x to the 1/3 is just another way of writing the cube root of x. They mean exactly the same thing. That's what that means then. That's how the fraction exponent works. If it's 1 over something, it's really some kind of root or radical. So we have two different forms for it, and we have to watch this. They mean the same thing, but we can write it in radical form, like your regular square root or some other root, or we can write it in this fractional exponent form. They're both useful for different things, different forms of the same idea. And the exponent rules work. All the other exponent rules apply to these things just like they did before. So the exponent form is useful because it works like other exponents, but the radical form is useful, especially if we're solving equations and stuff. That way of writing it is very nice. So we want to be able to go back and forth between those forms a little bit. And we're going to work mostly in radical form. We're going to go on chapter 8 stuff. It's going to be mostly in radical form, but sometimes it's handy to be able to write things in fraction exponent form down the road. So you should know what they both mean and be able to write things in either form. Now, if I have some other numerator, this was just 1 over 3, and you can see what happens to the 3. So if you're asking, and you should be, what happens if it's 5 over 3 or something like that? Well, we can apply this rule again about multiplying exponents, and x to the 5/3 should be the result if I take that 1/3 times 5. That's my multiplying exponent rule again. So if I wanted to write it in radical form, that's the cube root of x to the 5th power. Or you might notice, if you want to be extra clever about it, there is a second way of writing that would also come out the same way. If I have 5 times 1/3, that's also 5/3. So that's another way of writing the same thing. And that in radical form would be a cube root of x to the 5th. So that sounds the same, but it's a little different order of operations going on right there. That sounds like the same thing. And it actually is the same thing, but we're writing it a little differently. This is the cube root of x to the 5th, and this is the cube root of x to the 5th. That sounds a little tricky right there, but in this case, that actually is the same thing. The order of operations going on is different. If you remember our order of operations agreement, we did exponents and roots. They're at the same level on the order of operations. And that means you really do them all at the same time. And it doesn't matter here if you do the root and then the 5th power, or the 5th power and then the root. You're going to get the same value out of that. They mean the same thing. So you can write that whichever way is convenient for whatever you're doing. So if we're converting from fraction exponent to radical form, there's a couple different ways to write this thing. If we're converting the other way, you just got to keep track here. The power is going to become your numerator, and the root, what's called the index of the root, the type of root here, that's what becomes the denominator of the fraction exponent. So we can move things back and forth between those two forms. Not going to get terrible fancy about that, but I do want to look at some examples of that and see how these things work. See if I can get some out of the book on this. I think I have chapter 8 in front of us. These are in chapter 8 in the book. We're gonna kind of skip through chapter 8 and do some of the kinds of operations, but not get in too deep on this. There's a lot of things that are omitted by our course outline. And even among the basics that we are trying to get, I'm just going to slim that down a little bit because of the time constraints that we're under and the way this semester is going. We're going to try to get the basic ideas of it. The main things from chapter 8 that you want to be able to do are simplifying radicals to write them in simplest form and solve some basic equations with radicals if you run into that. We're going to do those next week. And then there's parts of chapter 9 that is where we end up for the semester that we'll get into. I'm trying to find the exponents, the fraction exponent form problems in here. They're kind of set up mostly with radicals. I'm going to make these up instead of working out of the book, I guess. I'm not finding what I'm looking for. Let me just keep moving. We got to deal with problems like this. It'll say convert to radical form. Something that's starting as a fraction exponent, like 3x to the 8 over 5. All right. In fraction exponent form. Something like the 5th root of x squared. I'm going to write another one down here because I want to think about how this works numerically also. Okay, so be careful with this. One of the common algebra mistakes that people make is getting mixed up on what the exponent applies to. I have 3x to the 8/5. There isn't any parentheses in there, so what is that power on? Power's on what it's immediately next to. That's an exponent on the x. The 3 doesn't really have anything to do with this, so that's just sitting there. It's 3 multiplied by whatever this is. So the 3 is not involved. The x, as the fraction exponent, has to be written in radical form. The denominator becomes the type of root that we're talking about. That would be a 5th root. And the numerator becomes a power on it. You can write that 8th power on the inside or on the outside. Whichever. Those are both valid answers to that in radical form. And going the other direction here, if we start with something in radical form, we can turn it into something with fraction exponents. This is a 5 right here. I can see that my handwriting's a little fuzzy, but this is a 5 out here on the index. So that's a 5th root of x squared if you say that out loud. But writing it in fraction exponent form, I just have to know the type of root becomes the denominator here, and the power here becomes the numerator. So that's x to the 2/5. One place where this might actually help us is if we wanted to calculate something like this. If we had a numerical instead of a variable expression, if I have a 12 in there, the cube root of 12 squared would be a little bit of a pain. When you have other roots on the calculator, it's a little bit of a pain to find that operation on the calculator sometimes, but your exponent key you're familiar with, and we can just do this calculation using the exponent key. So that's 12 squared, and then I want to take the cube root of that, and I don't think that comes out nice. So I'm going to use a calculator to do it, but the easiest way to enter it into a calculator is in this form. This is 12 base here, and the exponent is going to be 2 over 3. The type of root becomes the denominator, and the squared becomes the numerator. So that's 12 to the 2/3 power, and your calculator knows enough about that to do the calculations there with the regular exponent button, and that will work for that one. See how that works on the calculator. So see if I can get this visible, but I'm entering the base first 12. I'm going to use the regular exponent button, and I have to be careful here because the exponent's supposed to be 2/3. I want that whole thing to be part of the exponent, so I am going to use a container around that to make sure that that whole thing, 2 divided by 3, is part of the exponent. So that's what it ought to look like, 12 to the 2/3 power. And that's easier than doing a cube root on the calculator. It's just easier to get to. There is probably a cube root function in there somewhere on your calculator. Looks like it's easy to get to on this one. But that exponent button's familiar, and any kind of root can be done as an exponent. So if for some reason I needed to know the 5th root of 100, the easiest way to get to that is 5th root means a 1/5 power. So I just put the exponent in, not that. Exponent. 1. Yeah. I said 5th root, so that would be a 1/5 power. You just do have to be careful with the parentheses on that, because that 1/5 power has to all be part of the exponent, right? If I enter this as 100 to the 1 divided by 5 without those parentheses, then I'm telling the calculator to do 100 to the 1st power and then divide by 5, which is not what I meant. Right, we could do that in our head, because 100 to the 1st power is 100. That answer divided by 5 comes out 20. That's fine, but that's not what I'm trying to do here. I'm trying to do a 1/5 power. All right, so you have to make that difference. You have to use the parentheses or something to make sure that that fraction is in your exponent there. We're not going to do a ton of numerical stuff, but that is one place where the fraction exponent form is more useful, just because it's really easy to enter in a calculator. Good. Those are approximate values for that then if we needed them. Not going to try to get terribly fancy with those things. We're not going to see a lot of fraction exponent form now. I see it all the time, because working with these things in calculus, that fraction exponent form is much nicer to work with, but that's not where we're headed right now. So I'm going to go back to chapter 7 for a minute. I'm not seeing any questions on live here, so I'm going to go to chapter 7 and do some exercises with these equations. Again, I want to get some review in on that while we have some time today, and then intro to what we're going to do next week with simplifying radicals a little bit. We'll get into that. So here's the next topic, review. Try to get a little more practice on equations. We keep throwing in one more complicated thing and then solving equations with it. And in chapter 7, the new thing was these denominators. We had stuff like these kinds of expressions with fractions, with variables in the denominator of things, and that makes the equations a little harder to deal with, of course. So this is the kind of the pattern that we follow in this course. We throw in a little bit more complicated type of expression, and then we figure out how to solve equations that have that, or really how to get rid of that complicated thing in an equation. We solve equations by getting rid of the most complicated thing first. And most complicated thing here is, of course, that there's denominators in it. There's these fractional things in it. We got to worry about that. I got to finish the equation here. I left it blank there, but I wanted one that comes out kind of nice. So we're going to look at this. 1 over x plus 1 minus 5 over x is equal to negative 37 over 9x. So getting x by itself and that thing would be kind of a challenge. Most complicated thing is that it's got denominators, and we want to get rid of the denominators, just like we always did when there was fractions in it. We can multiply everywhere by something to get rid of all the denominators. So my first step is really to write this out. These are factors. And this one's simple enough that I don't have any factoring to do. They're already kind of written as separate factors, except I can think of the 9 and the x as separate factors here because they're multiplied. Those are the factors of all of this. The main thing I'm trying to do now is write it out with some extra space because I'm going to multiply them all by a common multiple here that has to include all of these factors. So it's got to have an x plus 1. It's got to have an x. It's got to have a 9 because their factors are the denominator. I don't have to put another x because I've got x already. Right? That's already contained in there. So I'm good on that. That's my common multiple, x plus 1, x 9. I'm just going to write them all separately. Take the time and write it out underneath or next to, not underneath, but next to each fraction so I can see what cancels on each one. It gets terribly long and then all the denominators go away. All right, so look at that. Scary looking thing. But here we go, simplifying it an awful lot. This x plus 1 is a common factor. This x is a common factor here. And both the 9 and the x cancel on this one. So my equation just got quite a bit simpler. Well, somewhat simpler. At least the denominators are gone. I just have to see what I got left now. So what I have left from all this is just 9x. What I have from this one is 5 times x plus 1 times 9. That's 45 times x plus 1. And this is negative 37 times x plus 1. So I'm not using it as a denominator here. I'm using it as a multiple because I get rid of the denominators entirely. I keep saying that because algebra students, although they complain about having fractions around, they seem to want to hang on to them in these kind of equations. And they seem to want to do this by like addition and subtraction methods. I mean, this is subtracting fractions. You could do a subtraction problem here. But that's actually a lot harder than what we need to do. That's actually making the problem, more complicated. And the equations have to go away. The fractions have to go away eventually. So it's easier just to get rid of the denominators first and then solve the equation, whatever you're left with from there. So I got this equation just having powers of x. And that's not even any powers. It's just x terms and number terms. So this is going to be a linear equation to just get the x terms together. Parentheses are the most complicated thing now, so I'm going to get rid of those. And then get all the x terms to one side and the number terms to the other side and see what we've got. So these are like terms on the same side. I got negative 36x from there. This is stuff we were doing now. We're getting some nice review here because this is equation solving from early on in the course. Once we got rid of the denominators, we're back to an earlier chapter kind of equation. This one's linear. I want to get my x terms to the same side and the number terms to the other side. So I'm going to get rid of these by adding 45 to both sides and adding 37x to both sides. That turns into just 1x. And that turns into number 8. So I got 1x equals 8. That's my solution to this. I do have to look back on these kind of equations to make sure that the number that I have as a solution is actually in the domain of this thing. I can't use numbers if they're going to come up undefined when I try to put them into the original equation. So I do have to check some stuff on this. I'm losing focus here a little bit. But I got 1x equals 8 or x equals 8. I'd have to look back at the original equation and make sure that doesn't make for a 0 denominator somewhere. But we're okay here. X can be 8. All of these things will be some kind of fraction, but no 0 denominators or anything like that. So I believe x equals 8 is correct. You can numerically check it if you want to do the calculations, but it works here. X equals 8 checks out just fine. So that's the process that we're going to use. I'm going to do a couple of these out of the textbook. Hoping that that's helpful as you try to work through this, and then we'll do a lead into next week's simplifying. So chapter 7 in the textbook, the solving equations part. I'm on it here. Exercise number 218. I want to look at. I'm going to copy this down, try to copy it down correctly, which is the first challenge in any kind of algebra problem, is copying it down somewhere where you can work on it without making a mistake about what it says. 1/4. See, we got to think a little bit about what factor means on this one, because we got some factors in the denominator, but they're mostly numbers here except for the c. So we got a factor of c, but we got to think about a common multiple of all of these numbers here. So I'm thinking about, what am I going to multiply by? And leaving some space to multiply by something. So I have the factor c, and I have these numbers. What is really a common multiple for all of these numbers? That's 12, 36, and 4. I could actually do 12 times 36 times 4, but I don't need to do all of that because 36 actually has 12 and 4 both go into 36, right? It's already got factors of 4 and 12 in it because 36 is already a multiple of those things. Try to get some good light here. So I do have to have the factor of c and a 36. Everything else will go into that. So that's all I need here is 36c times that, 36c times that, and 36c times that. I need something that contains all of those denominators. It is what you would use as a common denominator for this if you were doing that kind of question, but we're doing an equation instead. We don't want any denominators. We want a common multiple there, and then all the denominators should cancel on this thing, should go away. Let's see what we got. Well, the c is going to cancel here, and the 12, well, 12 goes into 36 3 times, so I take care of the canceling that way. That's just going to leave a 3 in that. That simplified a lot. The 36 cancels here, easy one. And here the c cancels, and the 4 goes into 36, so I can divide that out. 36 divided by 4 is just 9. That looks kind of almost readable there. I don't know why this is getting fuzzy. At that point, you have a great big long thing, but you just crossed off a bunch of it, so we shouldn't have that much left. Well, let's see what we got. C plus 3 times the 3 that's left. Oh, that got worse in focus, didn't it? C plus 3 times the 3 that I'm looking at there. Is 3c plus 9. And this one, the c and the c are left. That's c times c. So I do have a squared term in this one. That's interesting. And then over here, everything's gone except 1 times 9 is 9. I just have the number on that side. Now we're coming into focus. Hopefully that's coming into focus mentally, just like it is on the camera a little bit. But I do have a different kind of equation here. I have a squared term and a c term and number terms. So it's not linear. It's a zero factor property thing. I got to use factoring to get rid of that. So I'm trying to get a 0 on one side. I'm going to subtract 9. And I'm thinking 0 factor property. Or I'm actually writing down 0 factor property, so I'll remember what to do. Subtract 9 from both sides, you get a 0. Actually, you get 0 here too. I just have c squared plus 3c, right? Those in normal descending order. Factor that. Well, c squared plus 3c, it factors into just c. c plus 3, that's a regular GCF kind of factoring. And then the property says either c is 0 or c plus 3 is 0, in which case c is negative 3. So I have two solutions to that thing that work in that equation. But I have to remember on this kind of equation to worry about domain a little bit. And I have to look back at this thing. Good example of the problem that can come up here. If you go back to your original equation, if c is 0, I'm going to have a 0 denominator on some of this stuff. Some of these original expressions are undefined. So that can't be an equation. That can't be a solution to the equation because I can't plug it into the original equation and get a true statement. I get an undefined statement. So that's what they call an extraneous solution. It doesn't actually work. So get rid of that one. Now, if c is negative 3, that actually works fine in the original one. You can substitute in a negative 3 and you don't get any 0 denominators. So this one checks. Okay, we're going to have to keep an eye on that. So that's the risk that you take when you multiply both sides of an equation by something. It's a valid step to do what we did here and multiply everything by 36c, but it runs the risk of creating those extraneous solutions. If you multiply both sides of an equation by 0, that kind of messes up your equation, right? So if c was 0, this would be a problem. We didn't know the values then, so we do it, and we just have to check later and make sure that our values are actually valid in that. That will always be the case with these expressions, with equations involving rational expressions like these do. All right, hoping people find this later. I don't know if anybody's with me here. It's showing a couple watching, but let's see. I'm going to do a nice intro to this simplifying radicals thing because I'll give you a little head start on next week if you're watching this. This should hopefully give you a confidence level with what you got on this homework. You're doing, what is it, 7th online homework now, something like that. That's due Monday. That's just mostly these equations and a little bit with those fraction exponents and adding and subtracting rational expressions. So starting to see those come in. We got a lab to do with those also. And then one of the main topics for next week is this simplifying radicals. So I'm going to do a little intro to that. If you're catching this later, you can think through simplifying radicals a little bit. Here's the place that I start from that I hope illustrates what's going on with these. Start thinking about numbers and square roots. Radicals is this, anything with this symbol in it. It means a square root unless we put some other number on it to be a different kind of root. But I'm just going to work with square roots for now. So I'm going to write some of these things down. few different numbers right there. Now you could do all of those in your calculator, and most of them are going to come out to a decimal, right? This, if you do the calculations, this is of course 5. Hopefully when you look at the square root of 25, you think about 5, because 5 squared is 25. This thing is one that is a perfect square, because 5 squared comes out exactly 25. But that's the only one that comes out nice. That's the only one of those numbers that is a perfect square. So the others would give you decimal answers in the calculator, which is fine, but that's not the form we're looking for. We're not looking to get decimals now. We're looking to simplify them if we can. And that square root of 25, it's a lot simpler to just write 5 there. So the first question you ask yourself on simplifying radicals, you ask yourself, is it a perfect square? And if it is, then you can write it without any radical at all. That's obviously a much simpler way to write that value, is just write 5. So the perfect square ones are nice and easy, and we take care of that. If the answer is no, then we got to ask ourselves some other questions. Some of this simplifies a little bit here. So I'm gonna write down question number 2. We got to ask ourselves, is there a perfect square factor? So for these remaining ones, 24, 26, 27, 28, I have to think about the numbers, the factors of those numbers, to see if there's any perfect square factors. Now, perfect squares are things like 1, 4, 9, 4 squared is 16, 5 squared is 25, things like this. I could keep going, but we don't have anything that big. Those are perfect square numbers. So I have to look at what I got there. Is any of those things a factor of some of these? And in some cases there is. 24 can be written as 4 times 6. If you can write this using multiplication factors, like 4 times 6, if one of those is a perfect square factor, then we can separate that out. Here's the property that's going to help us simplify radicals. The big idea on this is if I have multiplication inside there, I can write it separately. It's not obvious that the square root of 4 times 6 is the same as the square root of 4 times the square root of 6, but it's true. Okay, that's the property that we have for exponents and radicals. If it's multiplying and dividing, you can do it separately. That's how we're going to take care of this. Square root of 4, I know what that is. So if I have a perfect square factor, I can turn that part into a number. So I simplified that as 2 square root of 6. That's a little nicer way to write that thing. We're looking to shrink the radical. That's our goal on these. And 6 doesn't have any perfect square factors, so that's as far as we can go with that. So now, here's the process. Again, if you ask yourself, is it a perfect square? If it is, then you can get rid of the radical because you have a nice square root there. If not, you go on to second question, is there a perfect square factor? And if so, we can shrink the radical like we did right here. We got to ask this on the other examples I have written down, but we're looking to shrink the radical. And then there is, eventually there's a question 3, but we're going to save that for later. Okay, I'm just going to do the simplifying now. Basics now. So question 3 is going to come later. That's a warning, but we'll deal with that later. 26. Now that's the next one on my list. This one we're done with. This one came out nice. 26 can be factored into 2 times 13, but neither of those are perfect squares. None of these perfect square numbers go into 26. So the answer is no on that one. That actually doesn't simplify at all. That's already as simple as you can get. The square root of 26, you're just stuck with the radical on that. Can't shrink it down. 27. 4 doesn't go into 27, but 9 goes into 27. So there's a perfect square that's a factor of 27. So I could write this as 3 times 9, but instead I'm going to write it as 9 times 3. I want to do the same thing, but I want my perfect square out first, written first, to the left right here, so that the number on the outside of the radical comes out in front of this. I'd rather have 3 times the square root of 3 than writing that the other way around. All right, it seems like a picky little thing, but I'm warning you on this because of the shape of the radical symbol, because of the way that it looks. I could write this as square root of 3 times 3, but if I'm doing this with handwriting and not super careful about it, it's easy for that thing to turn into, right? What if that 3 kind of gets pushed over a little bit and starts looking like it's inside the radical? Well, that's not the same thing as this if I draw my line a little too long. So you can easily get confused between these two things. And I don't want that to happen. That's why I'm avoiding that by putting the outside stuff on the left and the radical at the end of the expression. So there's a nice wall there between what's inside the radical and what's left outside the radical. That's the nicer way to write it. That's going to help avoid some mistakes on it. Now, just to verify what's going on numerically here, because we do have numbers in front of us. Clear this old stuff out. This is what I want to look at next. 3 times the square root of 3. I have to be careful in the calculator about what's inside that radical and what's outside of it also. So it's good to write the outside stuff to the left. That's 3 square root of 3. And you can see that comes out to 5 point something. That's what we would expect there. That is numerically exactly the same as if I just did the square root of 27 to start with. Square root of 27. That's the same value. Okay, it's just written differently. Written with a smaller radical. So there's no nice way to write this number without a radical. But when we do write it with a radical, we want to keep it as small as possible. Shrink that radical down as much as we can. That's the simplest radical form. So it's very specific what we're looking for here. Shrink the radical as much as you can if you can't get rid of it entirely. So 3 square root of 3, we're done. That's as simple as you can get. 28, I hope you've thought about this by now. What if we try to do this with 28? Is there a perfect square factor? It's not a perfect square, but there is a perfect square factor. A 4 goes into it. So this is 4 times 7. Now 28 separates into 4 times 7. Here's the big step, and I'm writing these down separately, but they're the same thing. I want to think about this. Now this is 2, and this is still square root of 7. So that's my simplified form there. 4 was a perfect square. Square root of 4 is 2. So I end up with 2 outside of the radical and the 7 left inside the radical. And that doesn't shrink any further. See, 7 doesn't have any perfect square factors anymore. So that's as far down as I can go. That's how that works with numbers. Of course, we're in algebra, so we're going to have variables in there also. And I want to introduce the whole idea with some variables in there. So hope you've hung around for this long. This is kind of long, but this is the next big idea. I'm actually going to keep those 3 questions off to the side. And I'm going to write some variable expressions now and ask those same kind of questions. If I have something like x to the 6th, x to the 7th, or x to the 8th. Okay, you get the idea. Radical expressions with powers in them. We're going to ask the same questions that we did before, but we have to think a little differently about what that means. Is it a perfect square? If you're looking at x to the 5th, then x to the 6th, then x to the 7th, and x to the 8th, what does it mean to be a perfect square then? A couple of them actually are perfect squares, and we got to see how this works out. I don't know, it's losing, seems like I'm losing focus again, but I'm not looking at perfect square numbers like 1, 4, 9, and 16 anymore. I have to think about what the perfect squares are for radical things. And x squared is a perfect square, and x is a perfect square, and x to the sixth is a perfect square. I say it's a perfect square because it's equal to something nice squared. That same exponent rule that we talked about with the fractions of multiplying exponents, that's the deal here. Anytime I can square something and come up with this, this is a perfect square. So any even number over here can be written as something to the second power. So all of those are perfect squares right now, including these two. They're both perfect squares, and all I have to do to get rid of the radical is divide by 2. 6 divided by 2 is 3. That's the simplified form of that one. Square root of x to the 8th is just x to the 4th. So we can get rid of the radical anytime there's an even exponent. Then we have a perfect square, and we can just get rid of the radical. Dividing the exponent by 2. And you can think back to this means. What the square root means is what? When I square it, will come out to x to the 8th, and x to the 4th is the answer, right? X to the 4th, when you square it, it comes out x to the 8th. So that works with our definitions of these things. Now, 5 and x to the 5th and x to the 7th, they're not perfect squares, so we go on to our second question here. Is there a perfect square factor? Well, there is with these things, because we can write x to the 5th using multiplication a bunch of different ways. But I'm going to write this as x to the 4th times x to the 1st. Using the adding exponents property to separate that 5 into 4 plus 1, because x to the 4th is the biggest perfect square that I can get out of there. So I separate that out. Again, that's can be done piece by piece because it's multiplication. It has to be multiplication. And then I can do the nice perfect square one. That's x squared, and I get 1 left on the inside. So that's my simplified, simplest radical form on that one. Gives you an x squared square root of x. And very similar with the 7 here. Now I could separate it 4 and 3, but x cubed I wouldn't be done with. I want to get this as much as possible. Shrink it as much as possible. So pulling out that x to the 6th is the way to go here. I'm going to split this one into 6 and 1. Multiply. Because I can get rid of the most that way. Square root of x to the 6th. Now be careful here about what's still in the radical and what isn't. Everything's still in the radical until you actually do the dividing by 2. 6 divided by 2 is 3. Now that's outside the radical. This is still inside the radical. So I'm putting that outside and this inside. Careful about how you write it. But x cubed times the square root of x. It's the same as square root of x to the 7th, but we've got it written in a simpler form. We want to get rid of radicals when we can. And if we can't, then we want to shrink them down as much as possible. And that's the technique that you take with that. So combining those ideas, if you have some big expression that's got numbers and variables in it, you can break that down using those ideas. This is evidently just a video that people will be watching later, so I don't want to make it super long. I'm not going to do a ton of examples because they start to look alike after a while. But here's the last idea that I want to tackle now. Preview to next week. If I have numbers and some variables in there and a big radical like 45 x to the 5th y to the 2nd. Trying to get simplest radical form of something like that. I'm trying to write larger, and the exponents are still a little small, but that's x to the 5th, and that's y to the 2nd. As long as all that's multiplied, I'm just going to think about it piece by piece. So you don't really have to write this down, but I am going to write this down. Illustrate what's going on. The magic behind simplifying radicals is this property that says you can take stuff apart and put it together. We'll have a little bit of putting together to do on this one. but you can separate things out as long as it's multiplying and dividing. Actually, it'll work okay. So now on each of these pieces, I ask myself my two questions that we have so far. Is it a perfect square? 45 is not. There's no nice number that when I square it, I get 45. If you don't know that right off the bat, you can try to take the square root of it, and it's not going to come out nice. It's going to be a decimal. For these, is it a perfect square means is it an even exponent? Is that number something I can divide by 2? So the answer is no here, and the answer is yes on this one. This is a perfect square, of course. The square root of y squared is just y. So to get rid of the radical on this piece, these are multiplied. Now, on to question 2 on these others. They're not perfect square, but they have a perfect square factor. Right? 45 can be written as 9 times 5. So I'm going to separate it out that way. I'm going to go ahead and write them separately. Perfect square and what's left when you separate it out. This one separates into a perfect square and what's left when you separate it out. So those are still in the radicals. I'm writing them separately. To shrink the radical, this becomes 3 square root of 5. This becomes x squared, square root of x. Those are all the pieces I have left. I shrunk the radicals as much as I can. 5 and x don't have any perfect square factors I can take out. Now they're shrunk as much as I can. The only thing new about these combined problems is we kind of want to organize the answer nicely using this same idea that I want to put the radicals at the end of this thing and everything outside the radical out in front. So I'm going to rearrange this as 3 x squared y and just pull together the radical stuff to go in here. The stuff that's left in the radical you can stick back together as the square root of 5x. We shrunk the radical a lot because we started off with 45x to the 5th y squared in the radical, and we end up with something like 5x in the radical. It's a simpler expression because the radical is shrunk down as much as we can. That's the idea on those. In the interest of concentrating on the basics with this stuff, I am going to concentrate on square roots. So if you were going on to deal with cube roots, you'd have to be looking for perfect cubes, and you end up having a little harder work to do on that. We're not gonna see cube roots enough to worry about it. I'm going to concentrate on square roots, the expressions. Not going to get much worse than this for simplifying radicals. The other idea comes into it. The third question comes up when we have fractions to start with. And I don't think it's going to be worth the time to press into that now. This really is a topic for next week. I don't think I'm going to try to introduce that now because I don't want to pile 100 different ideas into one video here. This is turned into a video people are going to watch later because I'm not getting any questions now. So I hope that's a good sign. I'm gonna close it off with that kind of simplifying. We will look at the fraction ones later next week. I will I'll have some stuff out Monday, and probably on Wednesday's video session we'll do simplifying different kinds of radicals like that and what happens when these are in equations. We're going to look at solving an equation that starts off with a radical in it. We want that radical shrunk as much as we can, and then we're going to have to figure out how we can get rid of that in an equation. That's not that hard to do, but that's a topic for next week also. So I'll save those for next week. Finishing off the lab and the online homework now. Let me know if you get stuck on anything with that. I'll be keeping an eye on the emails through the weekend and into Monday when those are due. Let me know what you're having trouble with there. I can put up some more stuff later if there's topics that you want a few more examples on, because I've kind of done one of each. You can go back and look at these, and then let me know if you want to see some more problems worked. I can put some stuff up later. Hope you all have a good weekend. Hope things are going well for you.